Let's use the table to answer the following probability questions. So what we have is we have various education levels recorded and various relationship statuses, let's say, that are recorded for a group of people. And the question is do you select a person at random from this collection of 665 people? What are the various probabilities? So the first one is, what is the probability that the person is married? Okay, so probability of being married, I'm going to call that P of M, is the total number of people is 665, so that's my denominator. And how many of these people are married? Because that'll be my numerator, the favorable outcomes of being married. So that would be the 408 total married people. And if you divide that out, you should get approximately, I'm going to say approximately 61.4%. And I'm just going to leave it as one decimal place for ease right now. What is the probability that a person is not married? Well, instead of trying to perform that calculation by counting up how many of these people are not married, why don't I just use a complement rule? So the probability of married complement is 1 minus the probability of being married. So it's 1 minus, I'm going to put this back into its decimal form, which would be 0.614, which is 0.386 or 38.6%. Now I could have added up these 84, 61, and 112 people to figure out my new numerator. Those would be all the people not married, but using that complement rule is a really quick, faster way to do that. What is the probability that a person has a college education or higher? So I'm going to call this P, and I'm going to call it C or higher. So still out of that total 665 people, how many have college or higher? Well, that total is actually over here. That's a row, so college or higher total is 143 people. Dividing that out comes out to about 0.215 or 21.5%. And again, you can do those divisions on your own, and I recommend making sure that you do those on your own and that you're getting the same answers as I get so that you know you are using your calculator correctly. Let's see if I can. Okay. What's the probability that the person is married and has a college education or higher? So now we're getting a little bit more interesting here. So an and. So what's the probability of the intersection between married and college or higher? So let's see, I'm looking for their intersection. I'm literally looking for their overlap. So if I follow this married column, if I follow that down and then across the college or higher, notice that the intersection there, the overlap is this 98 people, which now it's a little bit hard to read, but it is 98. So there are 98 people in that intersection out of 665. Dividing that out is approximately, turn these back into approximates, 14.7%. What's the probability that the person is single or married? So the probability of being single, union, married. Okay, we know from our probability rule before that we need to use an addition rule here. So we're going to take the probability of being single plus the probability of being married. And the question then is there anything to overlap from this formula? Can you be single and married at the same time? Well, no, you can't. So this will end up subtracting 0, but that's okay. So the probability of, let's see, single is this 112 out of 665, plus the probability of being married, which is the 408 out of 65, and then there's, 665, there's no way to be both at the same time. So this gives us 520 out of 665, which equals about 78.2%. Now I'm running out of room on my screen, so I'll have to bump my chart off for just a second. What is the probability that a person is married or has a college degree? So same formula, because it's an or, it's an intersection, so the probability of married or college or higher. By my formula, that's the probability of married plus the probability of college or higher minus the intersection of those, married and college or higher. So we've already calculated probability of being married, but I'm just going to write that back out. That was 408 out of 665. And the probability, so this comes from A, and then the next part is from C. The probability of having a college degree or higher is 143 out of 665. But there is an intersection here. These overlap, and we saw that here in part D. The probability of being both married and having a college degree or higher is right here. There are 98 people in that overlap, and right now we've counted those 98 people both here and we've counted them here. We've counted them twice. So we need to subtract them out one time so that those few people that have both qualities don't get double counted. That leaves us with 453 out of 665, which is 68.1%. So notice that it does matter. This was mutually exclusive. This was not mutually exclusive. And how that changed the probabilities, but that there's no harm in starting off with, and you should start off with that formula, and then subtracting 0, so be it. No harm done. Let's see, in a certain group of people, the probability of having blonde hair is 32%, and the probability of having blue eyes is 40%. The probability of having both of those features is 18%. So in this case, let's go ahead and draw a Venn diagram to illustrate this situation. Whenever you're drawing a Venn diagram and you have overlapping and and or pieces to it, the general rule of thumb is to start on the inside and work your way out. So start with the intersection, and if you have multiple intersections, start with the most intersections. So if you have 3 circles, start where they all 3 overlap. I only have 2 circles, so I'm going to start where those 2 circles overlap. So I'm going to start here. There are 18% of people who fall into that category where they have both blue hair and blue eyes and blonde hair. And then what you want to do is subtract to work outwards. Okay, so I cannot simply put the 32% right here because the 32% includes the 18%. Those people are also in that circle. So I now have more than 32% total people in this blonde hair circle. So I can't do that. What I have to do is I have to say, okay, there are 32% in that circle, but I've already put 18% in there. So what's left is 14% to go out here. Now those two values add up so that total inside that circle is 32%. Do the same thing with the blue eyes. There need to be 40% total people in that circle, but there's already 18%. So subtract that out. That means 22% of people fall out here. And then what's also important is to realize that there are more to be counted here, more people to be counted, because right now we have 14, 18, and 22%, but that doesn't add up to 100. So there's some people who fall out here who aren't inside any of those circles. So if I take 100% minus 14% minus 18% minus 22%, what's left to go on the outside is 46%. So again, you have to use that probability distribution rule, which says all the probabilities have to add up to 100%. So now we have everyone accounted for, and now we can answer questions. What is the probability that a person has blonde hair or blue eyes? So or. Well, we want anyone at all who is in any of these circles. So we have 14%, 18%, and 22%. That would be anyone anywhere in those circles. So it looks like 54% of people have one of those qualities or the other or both because of the inclusive or situation. What's the probability that a person has blue eyes but not blonde hair? Okay, so that I need to be inside the blue eyes circle, but not inside the blonde hair circle. So that would be the people in this part. They have only blue eyes but not blonde hair. So I can just read that off, 22%. What's the probability that a person has neither blonde hair nor blue eyes? So neither of those features would be outside of all of those circles. So that's the 46%. So you can see that if you create your Venn diagram first and you take the time to get all of the percentages where they go very carefully using subtraction, then you can answer a whole lot of questions about that very quickly.